We have seen a couple of extensions of the basic method for resolving redundancy. We moved the methods from the velocity level commands to the acceleration level commands, and we have seen that this extension enables us to consider also objective function which takes into account the dynamic model of our robot manipulators. The second extension that we have just seen is moving from a pure planning stage to a control stage in which we use feedback in order to recover possible errors in the execution of the task. We have seen that a simple proportional term to the error added to the desired task velocity is enough when dealing with velocity inputs, and a PD scheme is the one that is needed in order to recover the error when we are dealing with acceleration commands. Now we will see more extension. In particular, we start with the case in which we have a manipulator mounted on a mobile base, and we will consider mainly the case of a wheeled mobile base. In this case, we need to derive, if we are dealing with a problem at the velocity command level, we need to derive a suitable Jacobian of our structure related to the task that this robot has to do. And typically, to make things simpler, we consider that the task is assigned to the end effector, maybe the full pose or just the position or the position and pointing for the end effector of the manipulator. But indeed, we have more degrees of freedom in the structure because we have a moving base. So we have to compute the degree of redundancy in this case. And the main difference in the presence of a wheeled mobile base is that we need to make a difference between the number of degrees of freedom, so the number of generalized coordinates that will describe the full mobile manipulator, and the number of actual commands at the velocity level. So we deal essentially with a kinematic treatment of the problem. So here in the slide, you can see a mobile base. This is a Nomad 400X Air. It's a unicycle type robot. In fact, it has 3 differential wheels at the base, but they move in a synchronous way. And on top of which we have a Puma 560, a 6 degrees of freedom, all revolute joint manipulator. So we define a subset of generalized coordinates, the QB, for the base, and the usual coordinate, the joint coordinate of Dernavik-Hartenberg for the manipulator. We will call this QM, so that the full set of generalized coordinate is the vector Q, which will be of dimension n. For instance, we will have 3 coordinates for describing position and orientation of the base, and 6 coordinates for describing the manipulator configuration. So n would be 9 in this case. We define also a task variable, so the variable to which we assign some desired task behavior. So this will be parameterized by a function, by a variable r, which is a function of the configuration, and we assume that this vector r has dimension m. Of course, this will be a function of the whole configuration of the robot, not only of the manipulator, but also of the position and orientation of the base. However, there's a big difference between the 2 parts of this robotic system. In fact, we have seen that we can directly command, under suitable assumption, each individual coordinate of the manipulator, so that we can imagine that our velocity commands, qdem dot, are actually the possible input commands to our system. So there's an identity in case of the manipulator. This was our assumption for all kinematic treatment of the first order level. However, the base behaves in a different way. In fact, this mobile base has only 2 commands in this case. These commands may be parameterized in different way. We will see now an example on the blackboard. But essentially, you can imagine that this base can have a linear velocity and an angular velocity. And of course, you can combine them. So you have, in fact, only 2 commands, while the kinematics of the base is described by 3 coordinates QB. So you have a model of the base because of the presence of the non-alarming constraint due to the rolling wheel. This is something that you have seen in the course of autonomous and mobile robotics. So in fact, what we can command is not directly QB dot, but the set of velocities UB. So in fact, we collect this into a number of actuating variable. Let's call them NU, and NU will be in general strictly less than N, equal to N if all the commands are actuated, for instance, if you have an omnidirectional mobile base. So let's see this G matrix, which is has the dimension of the generalized coordinate of the vehicle, how it is, so the number of rows, the number of columns are the number of commands. Let's see one simple example of this situation. I think that you have treated this before, but suppose that we have a 2-wheel differentially driven mobile base. So we characterize the coordinates with its center position x, y, with some preferred direction theta with respect to the x-axis. So we have that QB will be x, y, and theta. So this locally at least lives in R3. Which are the commands? So we said that we can have a linear velocity v and an angular velocity omega. So the UB may be one of a different set of input. So this is the more, let's say, geometrical input. But of course, you may imagine also that your actual command are the velocity on the ground of the right and left wheel. So we have 2 motors. You can command VR and VL. Or if you have a motor mounted on the axis of the wheels, you can replace this by the right angular velocity and the left angular velocity omega r divided by r. No, sorry. This is, of course, not true. R omega r and r omega left, where r is the radius of the wheels, the common radius of the wheels. So you can use v and omega or vr, vl, or omega r and omega l as input. In any case, the commands are 2-dimensional. And now we can write the expression for the kinematic model, QB dot. The motion of the x coordinate will be cosine of theta times v, the linear velocity. Of the y coordinate will be sine of theta v, and the variation of theta, so theta dot, is directly omega. So in this case, you can organize this in a vector form, a matrix vector format. So you have cosine theta, sine theta 0, 0, 0, 1, and then you will have v omega, and this is in fact g of qb times u. And you see that we have 2 commands for the motion of 3 coordinates. And if you would like to use this other set of commands, there's a simple mapping that gives you the linear velocity will be simply the average of the right and left wheels. So if both wheels have the same speed, this will be the speed of the mobile base. If they have opposite speed, there will be zero linear speed. In fact, everything will be an angular speed. In fact, the angular speed is computed as VR minus VL divided by D, where D is the distance between the two, the right and the left wheel. So here we have a GQB that we will use inside this model. It's just one example. You can assume more complex bases like a car-like or a car with trailers and so on. But this is enough for our purposes to understand what happens to the possibly kinematic situation for this robotic structure. So let's take the task kinematics. So some function f of q. This will be a function of both, in general, of both the base variable, so the variable to the mobile base, and the manipulator variable. So if we take the first time derivative, we have a partial derivative of this function with respect to qb, and then of qb with respect to time, so we have qb dot, and the same thing for the other set of variable qm. Remember that every time we make a derivative with respect to a vector, each component of the original function f derived by the vector qb, for instance, will be a row vector. Okay, so this is a matrix with dimension m and number of columns equal to the dimension of qb. Same for the other. So we will call this, as usual, the Jacobian B is like a partitioning of the Jacobian of the task. So jb times qb dot plus jm times qm dot. However, qm dot are directly actuated, so we simply replace qm dot with the commands um, while the motion of the qb is subject to the non-aerodynamic constraints, so to a kinematic model like the one that we derived on the Blackbird. So we replace qb dot with the matrix G of qb times ub. And now we take out on the right-hand side all the commands, ub and um, and we obtain a new matrix, which is part of the task Jacobian, but one part of the task Jacobian is manipulated, let's say, by the matrix G, the kinematic model of the base. No matter how, this matrix, we will call this matrix a Jacobian of the non-aerodynamic mobile manipulator. Okay? So it's something that you can compute for your structure, depending on the task and depending on the mobility of the base. And of course, the task depending on the kinematics of the robot manipulator. So with this in hand, all what we have seen, I said most, but probably all of these previous results, so how to deal with possibly redundancy, can be tackled by replacing wherever you find the J with the non-aerodynamic mobile manipulator Jacobian. Okay? And wherever you find q dot, which were our original commands, suppose that we can command each velocity, in fact, is replaced by the actual velocity commands. And the degree of redundancy now, with this in mind, so we will have r dot equal j n m m u. So we have to look at the number of rows and columns of this matrix. This will have m rows and only nu columns, so the number of actual input commands, and u is strictly less than n. So the redundancy is there if nu minus m is strictly positive. So this is the index that characterizes redundancy with respect to a given task of a non-aerodynamic mobile manipulator. Let's see a couple of examples very shortly. This is not a unicycle type like that model base. In fact, it's a car-like type, so it's similar to the car with a steering front wheel. So the coordinates, the QB, in this case will be the position, let's say, of the rear axis, x and y, the orientation of the car with respect to the x-axis, so an angle theta, but also the angle of the steering wheel, because this will change the way in which we move when we apply a linear velocity to the rear or front wheels and a steering angle velocity to this front wheels. So we have, in fact, 4 coordinates QB. On top of this plate, on the top of this mobile base, we have mounted a planar, horizontal planar, to our arm. So there we have 2 additional degrees of freedom. And both joints are directly actuated. So we have a total of 4 plus 2, 6 generalized coordinates. But in fact, we have only 4 commands. The 2 commands to the joints of the robot and the linear velocity, whatever, front or rear wheel, and the angular steering velocity of the front wheels. So we have only 4 commands. So now we look at the task. The tip of the manipulator, something that lives on the plane, should follow a trajectory. Here you can hardly see a point, which is the starting point of the trajectory. This trajectory will be a straight line going across the workspace. So initially, the robot is placed in this condition. And in fact, the end effector is not on the initial value of the desired trajectory. So our scheme should include the presence of an error. So whatever we have done so far will include also kinematic control, since we are working at the first order level. So in terms of velocity, we will need a proportional to the error term added to the desired task velocity. But this, no matter what, we have to follow this trajectory in position. So the task dimension is 2. So m is equal to 2 and u is equal to 4. So the degree of redundancy is nu minus m equal 2 and not n minus m equal 4. Okay, this is the main difference. So apparently we would have had a larger degree of redundancy, but in fact, in terms of commands, we have only degree of redundancy equal to 2. Now, how do we use this? In fact, we used a scheme based on the projected gradient, and the function that you like to optimize is the maximization of the manipulability of the non-autonomic mobile manipulator Jacobian. So manipulability, remember, is the capability of transferring the command, the 4 commands in this case, and u equal to 4, into mobility of the end effector position in the plane. Now, if we had a fixed base manipulator, we know that when the arm is stretched, we have no possibility of applying a velocity in the direction of the stretching of the 2 links. But if this manipulator is mounted on a mobile base, of course the mobile base can provide a velocity to the tip even in the direction of stretching, unless the vehicle and the arm are orthogonal to each other. So this is the main direction of the vehicle that can, of course, steer right and left and progress or go back, and the planar manipulator is placed orthogonally like this. Because now, in the direction where the manipulator is stretching, there will be no command that has an instantaneous effect. Neither the joint velocity of joint 1 and joint 2, nor the linear velocity, nor the angular velocity, which will affect, in fact, this only later. So we have a singularity. So we would like to avoid this case, and by, let's say, intuition, if this is the singular configuration for the non-autonomic mobile manipulator, probably in this configuration, things go much better. In fact, we will see what happens. So if we run the simulation, you see that the robot will go back until the end effector is attached to the trajectory proceeds, and then the robot goes and follows, more or less maximizing its manipulability, so having the arm stretched in front of the vehicle. And you can see that the base has made a backup maneuver, but this was completely unplanned because everything is based on the scheme in which we invert the task velocity in the presence of redundancy. So this is a pure result of the scheme of redundancy resolution and of the compensation of error with the kinematic control on the task space. Here I have a completely different video just to show that things may be much different. You may hear some sound in the background. This was recorded at the Automatica Fair, one of the largest fairs in Europe in 2008. And it's a mobile-based manipulator with a very complex kinematics of the base. There are 4 wheels. Every wheel can rotate on its place and receive a velocity command. On top, you see the torso of the Justin bimanual manipulator, and this robot is following passively the motion imposed by the human, so it's dancing in a sense with the human. But of course, this is passive in the sense that the robot is not pushing, but receiving some forces transfers this into a change of the pose. You may have seen that the upper body changes a little bit, but most with the motion in the right direction of the wheels, so with the reorientation of the wheels. And here, if you count the number of degrees of freedom, you have this type of situation. If you don't include the motion of the arm, so just the torso, which is this value, and the actuated commands are 8, so they're moving only the wheels. Okay, so there is certainly some redundancy in this case, and you can see what happens with this coordinated motion. Okay, now let's move to another extension. So far, we have considered the specification of a task in terms of equality. So we have a Jacobian, we have more Jacobian if we have more tasks, we can augment the Jacobian, we can handle the task with an order of priority, but in all cases, we have relations of the type J times Q dot equal R dot. What happens if we consider the presence also of linear inequalities in the task problem formulation? So suppose that, again, our commands to be chosen are the joint velocity Q dot, and we have a set of linear constraints, J Q dot equal R dot. Of course, this is at the current configuration. So in this slide, all dependencies on Q has been eliminated. And then we have linear inequality of the form C matrix C times Q dot less or equal than a vector D. Of course, you can always rephrase inequalities in terms of less or equal, just flipping around the sign of things. In particular, you may also consider the equalities transformed then as a double set of inequalities, because if you impose that JQ dot is less or equal than R dot and JQ dot is greater or equal than R dot, then you will have 2 inequalities, and the second one you can change the sign and have it in the form of that inequality, but this is not the most efficient way of dealing with this constraint. In addition, you may think that there is some initial convex set on which you're choosing your Q dot, and this may start with the full n-dimensional space and then be restricted. For instance, in a task priority strategy, we have seen that the set of admissible solution is being restricted from one step to the other. Okay, so this is the setup. Now, how do we deal with inequalities? Let's go back to what we have done for the equality case. So JQ dot equal R dot. So we formulated a solution set in which we are looking for the minimum norm command, so joint velocities. And the solution set for equality is the one that minimizes, while Q dot belongs to the generic convex set, the norm of the error on the task velocity execution. And this set of possible solution in which we are looking for the minimum norm 1 can be built in the following way. Take one possible solution to this error minimization problem. Remember that it is not said that we are able to zero that error, but we are minimizing the error in norm. So take any of this solution, one specific one. Let's call this Q dot star, and all the set that minimize will be given by the Q dot, which provide the same value of J Q dot star, so the same value of R dot. Okay, this is quite obvious. If Q dot star was exactly solving this, then we will look only for other Q dot which solve the same equation. And there may be many if we have redundancy. Among this, we will find the minimum norm one. But if Q dot solves this problem at best, so minimize this, but is not able to bring this to zero, so no other Q dot will be able to bring this to zero, and all the Q dot that we consider are those that behave like Q dot star, so they gave the same error norm. Okay, so this is pretty much clear now that we have investigated the properties of least square minimization, so doing the task at best. So what happens when we are dealing only with inequality constraint? So we introduce a concept which is well known in operation research and in optimization methods for linear and nonlinear systems. We introduce so-called slack variables, so a set of non-negative variable of dimension m, as many slack variable as the number of inequality constraint, and we rewrite the constraint CQ dot less or equal than D in this form. Of course, if we satisfy the constraint, if we would satisfy with the Q dot the constraint, this would be 0. So CQ dot minus D less or equal than 0 is exactly the original constraint. But if this is not possible for any reason, with the Q dot chosen in the convex set to start with, then we start relaxing things. So we are adding positive level of this value, so we are violating some of this constraint, not all of the time, because some components of W may be 0, some other may not be 0, but in fact, we try to bring them all to 0. And if this is not possible, it means that we are not able to satisfy all inequality constraints, but we do this at best by using these slack variables. Now, with this in mind, the set of solution to this problem are given by one possible Q dot star that minimizes the slack variable in this, satisfying this relaxed constraint. Of course, if possible, if Q dot star is actually a solution of the original set of inequalities, W will be 0, and a Q star satisfies CQ dot star minus D less or equal than 0. But if this is not possible, we take the best possible Q star, the one that minimizes the slack variable, so that violates the least in norm the set of constraints. So this is one possible solution. How do we generate all them with the same idea here behind? So we look at the intersection between the convex set, because the convex set may always be there. If it's not relevant, then this is all the set of Rn, so no restriction at all. But in general, it's the intersection between the convex set. And then you look at the single inequality one by one. And if your Q dot star was satisfying equality J, so was giving Cj transpose the jth row of the matrix C times Q dot star less or equal than this scalar dj, then all other Q dots that you consider in the set of solution to this inequality should satisfy as well that inequality. If instead the Q dot star is violating one equality, one generic equality, the jth here, then you consider only Q dot star that gives the same result for that inequality, so that they gave the same violation of the Q star dot on the component Cj. Okay, so it's exactly the same thing. So introducing these slack variables, we can formulate the problem in a very similar setting by suitably defining this search set for solutions in a similar way. So if we put together inequality and equality, so we take the two objective function. Here there's no restriction, you see. This has only become a minimization of this task velocity equality constraint. And this is the objective function of the inequality case. And of course, you have to consider also the inequality. Pay attention, we have flipped over the things because now W are non-negative numbers which are part of the solution. So Q dot and W are what you are looking for. And then we brought W on the left-hand side so that on the left-hand side we have a matrix multiplying the variable of the problem less or equal a data of the problem. Okay? So it's exactly the same rewriting of this condition. And of course, we may start prioritizing constraint. So prioritizing the constraints which are equality, which are handled here, or prioritizing the inequality constraint. One is more important than the other. And we will see through example what happens. Of course, this is quite an advanced topic for a course at the master level, but it's nice to see what happens. So before doing this on practical example, I would like to present, as usual, some geometric view of what's going on in the presence of both equalities and inequalities. So imagine that we are in a configuration of our robotic system, and now we live in the joint velocity space. So we have to find velocity that satisfies inequality constraint and equality constraint as well. So let's consider this case. Suppose we have, well, here the gray is not really clear, but suppose we have two inequality constraints. So we should be above this line, this is one inequality, and above the other line. So the region where you see written feasible convex area from the inequality is the admissible region that satisfies the two inequality constraints. So you can pick any. This is the space of joint velocity. It's a two-dimensional space, but of course, this is only a visualization on a plane. It's hard to make more complex figures, but so there we are looking for a solution. And now we add an equality constraint. So a line crossing the feasible area, which by the way is convex because the inequalities are linear. So all set of solution that satisfies both inequality constraint and live on this line, so they satisfy also the equality, are given by the, this should be green, the darker, I would say, line on top of this picture. And now, this will be our set in which we are looking for the minimum norm solution, and the minimum norm solution will be, in fact, given by that vertex. The arrow goes from the origin to a point which is admissible for all constraints, and it's the smallest one that satisfies all constraints. So we live on the line, so on the equality, and we are inside. Actually, we are saturating one of the two constraints, while the other constraint is satisfied with some degree of tolerance. Okay? Now, this is a unique solution that the method of quadratic programming will find. And if we are now decide to introduce priority among these three constraints, the two inequalities and the equality, there will be no change no matter which constraint we are considering. So any priority order will give the same final solution. Why? Because there are feasible solutions to all constraints. So the order doesn't matter in this case. Wherever you add constraints, but you are consistent, so you don't exclude the existence of a solution which is feasible for all constraints, then the priority is irrelevant. Okay? It's like having sufficient resources for doing multiple tasks. Now let's see other situation. Let's see this situation, which is exactly the same as before, but in fact, I've taken this horizontal inequality 1, and I've flipped the sign. So instead of requiring to be on top of this line, we require to be at the bottom. The other inequality stays the same, so we require to be on the left. So the feasible convex area is a gray shaded, but hardly to see on the screen, but you will see it clearly in the video, this area. And now the equality constraint remains the same, and of course, it never crosses the feasible area. So in this case, there will be no exact solution, whatever you do. So if you're trying to solve the problem as such, without priority, you will typically end up violating all of them. So you may find a solution which is in this triangle, so outside the two inequality and not on the equality line. Very bad. Instead, if you're imposing some priority, you may not be able to satisfy all constraints, but at least the highest priority constraint will be satisfied. So suppose that we consider the equality constraint as top in the stack of tasks. So the first thing that we have to do is to live on that blue line. And then we will use this notation, this type of ordering symbols says that the task on the left has higher priority than the task on the right. So if you suppose that you take the equality as top, first highest order priority, and then you consider inequality 2 more important than inequality 1, so of second priority and third priority. So the solution that you will get will be the one given by the red arrow, which stays on the line because this is the top priority constraint, satisfy inequality 2 because this is more important than inequality 1, and of course violate inequality 1, but it violates the least possible, in the least possible way. So in this case, the slack variable of inequality 1 will be the distance between that solution and the closest point on the frontier of this inequality. This will be W1 because it's associated to inequality 1. And it's a positive number. We'll exactly give this distance. And it's the least possible distance that you can achieve while satisfying at best, in particular, exactly the first and second priority tasks. Instead, if you reverse the order of priority among the two inequalities, you will find this different solution. Now here, inequality 1 is more important than inequality 2, so you take the top equality constraint, you will stay on this line, and all these green points will satisfy also inequality 1, but you will take the minimum norm solution there because it's also the one that minimizes the distance from the violated inequality 2, which is now of the lowest priority order. Okay? So you see that things may change differently. Now, other situation may arise. So again, same set of constraints as before. We have an inequality which should stay in this area. The second inequality which stay in this area. So this area is the feasible convex set area. In addition, we have this equality. So also in this case, there is no exact solution. But now we consider other prioritization. So we don't consider only the equality as top, but in fact, this solution will be one in which the equality is still on top, but we make no preferences between inequality 1 and 2. So they are at the same level of priority. So we consider the two inequality in the second step of our task priority optimization method. So in this case, since we make no difference between the two, we will certainly find a solution which is on the top constraint, top priority constraint, the equality, but then we will find a solution that in this case violate both this equality, we are on the right-hand side, we should have been on the left-hand side, and this equality, we are on the top side, we should have been on the bottom side. But if you take the distances between the boundaries of these feasible regions, then the norm of this distance will be minimized. In fact, you can find this geometrically. You take you bisect this angle, and the solution will be with equal values of the weights, which is the one that minimizes under a linear constraint this norm, and is the one that intersects with the equality constraint, which is satisfied. Now, if you reverse things, so if you consider both inequalities more important than the equality, so the equality is something that you would like to do, but if possible, in a sense, so you will stay inside this area. All Q dot will satisfy both inequality, which are the first priority task as a whole, and this is higher priority than the equality, so this will be violated because I will not exceed my feasible area, and in fact the solution that I found is the closest to the equality, so minimize the norm of the error JQ dot equal R dot, so the equality constraint in this case. You see that you can generate different possible solutions by considering different priorities in your set of equation and linear inequalities when you don't have an actual feasible solution for all constraints. Finally, a very special case here, I'm considering a different situation than the previous three. So I have three inequalities, 1, 2, and 3. I should be on the bottom, on the bottom, on the bottom. So this is the feasible convex area. And again, there's no solution because in this area, the equality constraint does not cross this area. So we cannot satisfy all four constraints, 3 inequalities and 1 equality at the same time. So what happens for the solution set? They are not exact solution, they are minimizing some norm on the constraint error. So let's see, depending on the priority that we give, we may identify here different solution set in which we look for the minimum norm solution. So for instance, if the equality, this line, being on this line, is more important than all the equalities, no matter in which order, then the set of solution will stay here. So we'll satisfy the top priority constraint, the equality, and in this case we'll satisfy both inequality 1 and 3, and we'll minimize the distance. You see that this is a special case numerically because this equality is parallel to the inequality 2 when the inequality becomes active, so it becomes a strict equality. So any point here will satisfy 3 constraints and will minimize the distance from inequality 2. No matter which order you're giving to the inequalities in terms of priority, you will find the same set. And inside this, for instance, if you're minimizing the norm, from here you will take this solution. I'm not drawing this in order to not make much confusion. Whereas if the inequalities as a whole, or one by one, have higher priority than the equality, then you will stay in this area, so you will satisfy all of them, and the solution set will be given by this line, which is parallel to this one. Again, all these points violate in the same way, the minimum possible way, the equality constraint. So they have the same distance from the equality. And again, if you're minimizing the norm of this set of approximate solution to our original problem, because we are violating, so doing at best also the equality task, we will take this point, which is the minimum norm from the origin of our velocity space. So I think that this covers a number of situations geometrically. Of course, there are numerical algorithms that performs the optimization in the presence of linear and linear equality constraint and linear inequality constraint plus possible convex set. And there are software packages which do this for you and which are specialized to this robotic application. In the bibliography at the end of this block of slide, you will find references and also to available freeware packages developed by researchers in the field. Okay, so let's see some example. This is work done in our lab a few years ago. So here we see some simulation first and then one simple experiment with the 7R KUKA lightweight robot. And the simulations are very instructive because they are pretty much simple to interpret. So we consider a 6R planar robot doing some point-to-point task in the plane. So these tasks being in one position in the plane is a two-dimensional task. We have 6 degrees of freedom, so we have a degree of redundancy 4, but we consider also some inequality constraint. And the inequality constraint, we'll see, will be on the position of one particular point in the serial chain of these 6 links. And we consider this inequality as being a hard inequality so that we cannot violate it, or a soft inequality, which can be handled as in the previous case. The hard satisfaction of inequality is not included in the previous case. We will satisfy hardly, so exactly, inequalities if these are sufficiently high in the stack of tasks and we have not used up all of our resources. Okay? In general, you may expect that some of these inequality are violated, so they can be considered as soft inequality. But this will be clearer when looking at this simulation. So again, we have a 6-planar robot arm that has to accomplish a point-to-point motion with its end effector. And there are upper and lower positional constraints on the tip of the 4th link. You see that the robot is moving its end effector from that point to this destination point, while the 4th joint, actually 1, 2, 3, 4, the 5th joint, so the end of the 4th link, never exceed that area. Okay? Now, the second scenario, so this is feasible and hard inequality constraint. Now, this second situation is a different task, point to point and then to a next point. And in the previous case, we consider the inequality constraint hard. So you see that while approaching along a straight path, because this is in fact the result of a kinematic control law, until we are in a singular configuration for the task with this constraint. So we cannot reach that point. We stretch, the error remains, and now the system is moving to the next point, which is below here. Here you can see another representation of the distance to the constraint. And you see that in this case, since we are softening this lower bound, then we do the task as long as possible satisfying, and then we violate because we want to achieve the final point. So this idea and all the details are in this paper, which is referenced in the bibliography. And this is an experiment in which the 7 degree of freedom KUKA manipulator is doing a spiral in this Cartesian space, and you can see here that the motion are constrained. In fact, we are constraining the distance of any configuration from one initial configuration. And these are hard constraints. And you see that the evolution of all the joints, there should be 7 in this with different colors, remains always within bounds from a value which is different between each joint, which is the value of that joint in the initial configuration. Okay? You see that this is another way of handling inequality and equality, because the equality is specified by the fact that the end effector should follow that spiral in the 3D Cartesian space. So we have in principle a task of dimension 3, 7 degrees of freedom, all that can be actuated. So we have a degree of redundancy equal to 4, but we have inequality constraint on the joint motion, and we treat them in a hard way in this case. So this is another example with a humanoid, but the humanoid is not moving his feet, so we can consider this as somehow a fixed-base manipulator. And this is why I'm presenting this very nice video by the French group of LAS CNRS in Toulouse. So here they are considering tasks for a humanoid, and there are several tasks that you can consider. Each of these can be locally described by equalities or inequalities of the linear type on the joint velocities, and you can consider different order. For instance, you want to avoid the obstacle with the whole body. You want to gaze with the eyes of the humanoid to an object. You want to reach the object with one of the two hands of the manipulator, and so on and so on. One additional special constraint in case of humanoid, even if it's not moving his feet, and this is different from a fixed-base manipulator, which is anchored to the ground and will never fall, will never lose balance. In fact, the humanoid can lose balance. And if we consider this as a completely static task, so that we don't move at fast speed, in fact, we can move, but without changing our supporting surface, then the balance is a constraint that says that the vertical passing through the center of mass of the humanoid body should fall in the supporting area. And you can imagine that this projection should stay in some area. You can approximate this area with a convex polygon, and these are linear constraints of the inequality type. Okay, so this, I would say that this is placed on top of everything. We don't want the robot to fall. So this will be the top priority in all following experiments, but or simulation. But then you will see in different cases the switch of priorities give rise to different behavior of the humanoid. So let's see the first task. So avoid the obstacle is more important than look and reach. This is the obstacle. The humanoid is looking at the object and tries to reach with his hand the object. You see that tries to reduce the error is slowly reducing thanks to the fact that he's balancing with the other hand so that he can reach closer the destination. Now, the second and third task have been given a different priority. Still, you would like to avoid the obstacle as first. Actually, at 0 level, you would like to keep the balance. And now you relax the fact that you're looking at the object. You see the robot is looking there. But in this way, he can stretch better and avoid the obstacle and reach the destination. Now, in this scenario, reaching is more important. And for the time being, you don't consider this green box. And the secondary task will be looking at the object, again, while keeping balance. And in this case, you can do all them together. Now, reach, look, and avoid the green box are the three tasks in the priority order. So reach is the most important one. Look is the second one, and avoiding the box is the third one. So far, you're satisfying all constraints. Now you enter while looking, and then you enter and you still look, because avoiding the green fictitious obstacle is the lowest priority task. And of course, you may have changes the order. You may have not reached, if you put avoiding constraint at the first highest priority task, of course, the hand of the robot will stop in the closest position to the destination, which is inside the box, so it cannot be reached because you would violate this inequality constraint. Closest while preserving balance, static balance. And you may or you may not look at the object or not, depending on the priority that you give to this additional task. So I think that this is sufficient to understand that this is a very rich subject. In fact, it's a very active area of research and of finding solutions for more and more complex problems, no matter if humanoids or manipulators with enough degrees of freedom to be redundant for the tasks. Okay, so last topic for today will be how we deal with hard limits, like the one that we have seen in the before last video, that cannot be violated and that are defined for simplicity and also for practical purposes directly in the joint space. Actually on the variable that we command or on their derivative or integrals. For doing this, we developed a few years ago an algorithm, very efficient algorithm, which is called saturation in the null space method. So that uses redundancy in an active way in order to do the task while satisfying the constraint. And this constraint, this hard constraint in the joint space are relatively simple, are box constraint, how we used to say, but really are taken out of the priority list. So the priority in this algorithm are only of the equality type, and the inequality are only hard constraint on the motion of the joints. Typically joint range, joint velocity limits, if possible, joint acceleration limits of the box type. So an upper and a lower bound for each of these variables. So this means that our robot has limited capabilities, maximum velocity, maximum joint range, acceleration. We can develop this also at the torque level. We have seen how to move up things to the acceleration and thus to the dynamic torque bounds. So we assume that these limits are box inequality. They should never be violated, and they are not put into the stack of tasks. Now, this is a very critical difference. So we guarantee that these are always satisfied, and we don't need to care about their position in the stack of tasks. Of course, there will be other equality constraints which are handled with priorities. So we would do at best the first one, or exactly the first one, the second one, the third one, probably we cannot do it, and we will minimize the error norm on that task, and so on, in any case, while staying in the feasible set of the hard inequality constraints. So in order to guarantee a solution, we need to consider, in this case, also the possibility of relaxing the equality constraint. This relaxation, especially if we are dealing at the velocity level, but the same is true at the acceleration level, can be seen as a scaling in time of the desired velocity. So suppose that our equality task is moving along a Cartesian path with our end effector with some speed, high speed. And of course, high speed would mean high speed for the joints. And if this violates the hard constraint, there's nothing to do. I mean, we would not like to execute the task minimizing the norm, the geometric norm of the trajectory error. We would prefer to say, okay, let's scale down the speed of this task so that we do the same geometric path, so we go along the same direction at every configuration, but with a lower speed. So this is again a relaxation, but of completely different type than the one that we have seen so far in the hierarchical quadratic programming framework. So this method considers also the execution of equality tasks that possibly will be scaled when we don't have enough robot capabilities for doing the task itself. And this should be done automatically and with the least possible scaling. So how does our method work? We start again with a minimum norm solution. If this works and satisfies all inequality constraints as well, then we are done. But we typically end up with something which is unfeasible with respect to the hard constraint. So we need to modify this solution And probably we need to bring some overdriven joint, in which the minimum norm solution would give a velocity which violates its constraint, to bring it to its saturated value, so to the maximum possible value, and to leave this joint velocity as such, and try with the other joints to satisfy the remaining task, or the original task. Okay, so we will have a saturation, and we will see that removing joints velocity that saturates is equivalent to putting something in the null space of the original task or of the modified task once you see the contribution of the saturated joints velocities to the original task. And that will be more clear when we write down equation. So the nice thing of this algorithm is that it's online. So it doesn't require any future. It's a local method, okay? And it's a local method that generates always a solution, because in case of need, we will scale things. And if things are very bad, this scaling will bring the task velocity to 0, so we don't move, but we are satisfying so far the inequality constraint, so we are still feasible, although we relaxed completely the task. So this is a limit case. And this decision is online, and also to decide which joint we will bring to saturation, so how to modify the solution, and how do we do the following compensation for this saturation in such a way that we don't affect task execution, or if this is not feasible, certainly not feasible, then the algorithm SNS, saturation in the null space, will embed an automatic scaling factor, the least possible scaling, so closest to 1, which means no scaling, 0 means no motion, in order to preserve at least the instantaneous direction of task execution. Do not deviate from that in a minimum norm error sense, okay? So the general solution will take this form. So the SNS joint velocity command will be the Jacobian of the equality task, pseudo-inverse, but this Jacobian will be multiplied by a diagonal matrix of zeros and 1, which selects which velocities contributes to the execution in full, and which are being saturated because they are violating the hard bounds. There's a scaling factor S in front of the task velocity. Here I use the notation x dot. We used r dot so far, but it's okay. So if S remains to 1, we are doing the original task velocity exactly. If S is reduced a bit or more, we will do the same direction, but with a lower task speed, okay? And we would like to keep the variation the least possible, if possible, no variation at all, so S equal to 1, or S close to 1, okay? And then a term in some null space. The null space is generated in this way. You have the original Jacobian here, but here you have the Jacobian multiplied by this selection matrices, and we will see how this works. Essentially, again, it's the one that takes into account which are the saturated joint and which are not. And each time we saturate a joint, we'll choose the null space vector by fixing the joints saturated at their maximum or minimum value in this box constraint. So this is the general formula. We'll see how to get there with an algorithm. But before doing that, let's see geometrically again what happens with this algorithm. It's quite simple. So here we have, again, we're considering a two-dimensional space just for a matter of representation. So Q1 dot and Q2 dot. We have one linear constraint, so we have redundancy because we have two joint velocity and one equality constraint. And we have hard bound, so inequality bound, so we state for Q1 dot not larger than this and not smaller than this. You see that this is a symmetric bound of the box type with respect to the 0, and same for the Q2 dot. Of course, this maximum value needs not to be the same. In fact, this is not a square, but it's a rectangle. So we should be inside the rectangle, and at the same time on the line, which represents the equality constraint. Of course, here we have a solution. We see all this point in this segment are solution, and we would like to find the minimum norm 1, so the closest to this point. And we will do this in this way. First step, we find the minimum norm solution without taking into account the hard constraint, and you will see that we end up with this joint velocity, so with this point here, which is violating the constraint on Q2 dot, but not on Q1 dot. So one constraint evaluated, the other not. So there's no choice to do here. We simply have to bring the Q2 dot velocity to the closest limits. To bring it, this is overdriven, we are bringing it to its saturated value. And of course, this solution is not yet correct because we have not moved Q1 dot, which was originally chosen as being the minimum norm solution on the equality. So we have to compensate now the saturated velocity of joint 2 with some command. So we will moving just the Q1 dot until we encounter again the equality constraint. So the SNS solution will be given by this, and it's the minimum norm 1. Quite simple in this case. More general case with multiple overdriven joints and deciding which to one by one possibly bring back to their saturation is let's say, outcome of the algorithm. Let's consider another situation. Same situation, hard bounds with the box inequality constraint, so the same as before, but now we have a task which is farther away. Probably the R dot is larger in this case. This is a scalar task. We have two velocities, so again, we have redundancy. So if we apply the algorithm, what will do the algorithm in this case? There's no solution, no exact solution. So first, we will look for the minimum norm solution, so we end up with this. Again, we have Q2 dot, which is overdriven, while Q1 dot is inside the boundaries, because it's inside this stripe, this vertical stripe. So we bring back Q2 dot to its saturation level, and then we adjust by reducing the error with respect to the equality constraint, also Q1 dot. So we move up to there. More than that, we cannot go because we would violate at this stage the bound on Q1 dot as well. So the algorithm does the following. In the original case, we have some task velocity. X dot is the way in which we called. Now we scale this task velocity, but only because we know that there is no feasible solution. This is an outcome of the algorithm itself, so it does the scaling only when needed. So the minimum scaling is using an S which is less than 1, which will bring closer this line to the region, and in fact, until we get to the corner of the feasible region, and this will be the solution of the Q dot SNS method. So in both cases, the red line can always be constructed as the sum of one particular solution without respecting the constraint, sorry, the hard bounds. So on the equality constraint, then if you take that line and you take the parallel to the line passing to the origin in both cases, the correction from here to here is always given by the solution inside the null space. So this is why you can reformulate this algorithm as a null space algorithm, but which handles not some objective function, but some hard constraint in the joint space. Okay, so let's see one numerical case in order to understand why this is good and why this is in particular better than just scaling the task if we realize that the velocity that we are generating are too large at the joint level. We just scale the task without caring of saturation or not. Okay, so let's consider a planar 4R arm, and the task is assigned for the end effector position. So we have a differential map, which is specified by a task Jacobian, which is 2 by 4. And if you are using the Denavit-Hartenberg relative coordinate, the Jacobian will be this one with this shorthand notation. For instance, S1, 2, 3, 4 means the sign of Q1 plus Q2 plus Q3 plus Q4, and so on. And this is a local method, so I will show you what happens if we are in some configuration and the end effector velocity needs to be in some direction with some intensity, and how we solve that problem. Before doing this, we have to introduce bounds on the joint variable. In this case, I'm considering the simplest situation of box constraint only on the command, on the velocity, joint velocity commands. So all are bounded. The first joint and the second joint have a maximum of 2 radians per second. The third and fourth joint, which move less mass in a sense, have larger velocity limits equal to 4. So let's put the robot in a special configuration, one where we can do easy computation. This is just an exemplification of how the method works. So the configuration is the one given above, pi over 2 minus pi over 2, pi over 2 minus pi over 2. So this is the configuration. In this configuration, we evaluate the Jacobian, so it becomes a matrix of number, 2 times 4. We call the single column J1, J2, J3, and J4, because we will use this notation later on. And this red arrow, not in scale, of course, represents the velocity. And it's, in fact, a negative component along the x1 and, along x1 and negative component along x2, minus 4 and minus 1.5. This is the correct direction. The scale is irrelevant. Okay, so we should find the q dot which satisfy the bounds on qi dot I in absolute value less or equal than vi, capital Vi, while doing this task. So we start hoping that we will get, with the minimum norm solution for the joint velocity, a feasible value of velocity. So this is the pseudo-inverse of that Jacobian times this task velocity vector, and this will be in radians the velocity of the 4 joints. And you can see that if we didn't have any constraint, hard constraint in the joint space, this would move the first joint counterclockwise, the positive 2.45, the second clockwise, the third counterclockwise, the fourth clockwise, in such a way that the end effector goes in this direction and has the correct speed. But we have limits, and in fact, 2 joints in this case saturate, are overdriven, goes beyond what the robot can do. So if we command to our low-level control scheme these velocities without knowing that they are not realizable, the best that the controller can do is to give their maximum admissible value, so to have 2 radians per second for the first joint and minus 2 radians per second, the closest saturation, for the second joint. And if we do this, we will completely miss both the intensity and the direction of the desired task velocity. So this is not good. Not doing anything, not caring about the presence of this constraint. So the standard solution in this case was doing direct task scaling. So without caring about which joint saturates or not, to reduce the speed of x dot, so introducing a scaling factor less than 1 to x dot, you can put this in front. Everything is linear, so scaling the task velocity will scale equally the joint velocity. So you take the most violating one, you have to bring this back with respect to this ratio, with respect to its bound, to its limit, and the scaling factor is easily computed as 0.81. So you're giving up 20% of the speed, but keeping the direction of motion. And the solution is this one. You see that everything is brought back to the limits. This should be inside 2. This should be inside 4. They were already inside 4, but they are necessarily brought back because you're scaling all the motion at the same time, so all the joint velocity as well. So what you're doing with this blue solution, you're going in the right direction, but you're 20% slower. Instead, the SNS method does the following. There are two joints which are overdriven, joint 1 and joint 2. It takes, in this case, can be motivated, but it takes the most violating velocity with respect to its limit. So the joint 1 is 245 over 2. Joint 2 is minus 2.13 over minus 2. So indeed, the saturation is more critical for joint 1. So we bring joint 1 to its saturated value, the closest, in this case, the positive value, V1 equal 2. And we fix this. And now the remaining joint velocity needs to be recomputed because we have to take into account that joint 1, now it's gone, and it's saturating at 2 radians per second. So it's contributing to the original task with J1 times Q1 dot, which is equal to V1 dot. So the original task is partly done by this action, which is now chosen. So what we have to realize with the remaining 3 joints is this new velocity, which is the original one modified by the presence of J1, V1. So we have a new problem in which we have now still a 2, but now 2 by 3 submatrix. So the last 3 columns of this matrix there, multiplying the 3 joint velocity, this should realize this velocity. And we start with a minimum norm solution for this restricted problem. And in fact, the final solution Q dot SNS will have Q1 dot fixed at its saturated value. This was recognized from the first solution. And then you take the pseudo-inverse of this restricted Jacobian times the modified task, which takes into account that something has already been performed by the first joint in saturation. So this will be, this is written as a row, but in fact it should be a column. So this is the first component, and this is the last 3 components once you transpose this term. So the final result will be this one in green. You see that we modified, actually we increased in both cases the motion of joint 3 and joint 4 by bringing into saturation the most violating joint, and in doing this we have also reduced suitably the velocity of joint 2, which is no longer in saturation. If this was not the case, we would iterate or stop and scale the task because we know that it's unfeasible. So with this green line, green solution, the SNS, we will exactly, now the green arrow is superposed to the red arrow because we are doing the task exactly in the desired direction with the desired intensity. So something that we would have given up if we had performed simple task scaling. So in this simple example, we consider only limits in the joint velocity. In general, as I said, we can have upper and lower bounds on the joint variable, so joint ranges, and then upper and lower bound on velocities, upper and lower bound on acceleration. If needed, you can move this up to the dynamic level by setting upper and lower bounds locally on the joint torques. Now, typically, the bounds on the joint ranges is not symmetric with respect to 0, while the other are symmetric. This is why in the previous numerical example we have considered the absolute value of Qi dot being limited by Vi dot, which means that it's between minus Vi and plus Vi. So we are considering this case. Now, from all this set, we can, for the problem formulation, we need to have at a certain configuration, at a certain instant of time, while the robot is moving, remember this is a local method, an upper and a lower bound that may change over time for the joints. And we can compute the highest lower bound and the lowest upper bound by combining the three inequalities above. So we will take the highest lower bound for joint I as the maximum of these three numbers, which include, of course, minus VI max, so the bound directly on the velocity. And this is the bound coming from the joint range, which simply says that if t is the sampling time, and we will keep this command for an interval of sampling t, then with this speed, we may reach or not the lower bound for the joint I. So we give a limit. This is the maximum velocity in this configuration that will keep you inside the joint range. And same for the upper bound, and we take the minimum of these values. The third scalar in this set is instead a limit coming from the acceleration constraint. And this is treated in a slightly different way. These are, we associate a bound on velocity, which is coming from the fact that we cannot accelerate or decelerate more than the A max values, but we need to, let's say, limit the velocity in such a way that with this acceleration we could stop the motion in one step. Okay? So this is a simple computation that can be done, which turns out to give another contribution. And then you take the maximum and the minimum, and you have the strictest limits to your joint velocity, which is the variable that you have to choose in your first order method. So for instance, here, I'm looking at one generic joint, and suppose that the limits are minus 1.5 and 2 in position. So this is the limit in position, between minus 0.1 and 2. And within this limit, we have what is the actual limitation in velocity. So we should be inside the original bound, so absolute value of qi dot less or equal than 1.5. So we should be between minus 1.5 and 1.5. But then the presence of this constraint and the induced presence of this constraint on velocity will take out some part of this rectangle because we need to limit velocity so that we anticipate the fact that we may reach the bound in position, or we may not have enough acceleration to decelerate the robot to a rest situation in case of a safety alarm or something like this. So you see that this is the actual feasible region that we have. Now, if we are in some value of the joint position at a given time, for instance, if we are here, the limit will be given by that. If we are close to the boundary, you see that we restrict the velocity, in particular, close to the negative boundary. If we are close to the positive upper bound, we will restrict positive velocity so that we ensure that we will not get out of the hard joint range in the next step. Okay, so the algorithm works as follows. We will simply comment blocks of instruction, and I leave you this for a deeper investigation at home. So the first part is the initialization of the algorithm. So we start with the diagonal matrix W with all ones, which means that all joints are enabled for doing the task. If one joint velocity will saturate at a certain point of the algorithm, then we will bring the associated diagonal element of W to 0, which means that this joint is no longer used, it's in saturation. It will contribute somehow to the final task velocity, but it's saturated so that it will stay within its bound. Qn dot n at the beginning is the null space term, so it's included all saturated velocities in a vector form. So initially there's no saturation, so Qn dot is initialized to 0. And S and S star are the current task scale factor and the largest task scale factor computed so far. So this is kind of intriguing because the algorithm computes on the way some potential relaxation and uses only the least possible relaxation when it exits in the loop. So initially, the current task scale factor is 1, so we would like to make the original task. And the largest task scale factor is computed so far is 0, which means that we will try to increase this from 0 to 1. When we are able to bring it up to 1, then we will realize the original task completely. If not, we exit the loop of this algorithm with the best possible scaling. So the whole algorithm is within a repeat until loop, and this repeat until you find that there's no limit exceeded. So this condition is true. So you start saying that this condition is false, that you're exceeding some limits, and then you will reset this if instead you're saturating. So the second step is you compute the joint velocity. So with the first time you enter in this loop, of course, Qn dot is equal to 0, W is the identity, so you're computing J pseudo inverse X dot, and this is your candidate. If this satisfies, you exit, because the exceeding limit flag is false, so you're not violating any hard bounds, and you can go out. The second part is check if, in fact, some joint velocity bound is violated. And if this happened for even only one of this joint velocity, then you set the flag of exceeding limit equal to true. Then you build up two vectors, and you pass this vector to another sub-algorithm, we call this algorithm 2, which will compute the best task scaling factor and also the most critical joint that should be brought to saturation then, because we are violating things. So it could be only one or more than one, and if you have more than one, then you have to decide which one, and this is done by algorithm 2. Now, this is building up the current solution. When you return from this task scaling algorithm, you save some intermediate solution. This is the best that I can do so far. If I cannot do more, then I will exit this solution. So you're building the correct value of S star, V star, and Qn star in the algorithm. Finally, always coming back from algorithm 2, you know which is the most critical joint, because you enter that part, because your current solution was violating some joint velocity, and so you saturate that joint velocity. So J is the most critical joint. So one joint at a time, pay attention, this is very critical to avoid self-loop of the algorithm. So if we were exceeding the positive limits, we will bring it to the positive limit. If we were exceeding the minimum or negative limit, we will bring it to the minimum limit, and we will disable that joint through the weighting matrix W, so at the diagonal position J. Now, before proceeding, we need to check if it's possible at all to use the remaining joint for doing the remaining part of the task once we have saturated some number of joints. And this is done at this point. So you look at the rank, not of the Jacobian, but of the Jacobian multiplied by the weighting matrix W. So you zero out the columns of the Jacobian which are associated to joints which are saturating. So with the remaining joint, you hope to have enough rank to execute the task. So this is a conservative way. You may look if, in fact, the residual task is in the range of this reduced matrix. This would be a more correct approach. But here, to simplify things, you just check if the rank is full or not. If it's full, you can continue. If it's not, you have to exit with the actual solution. So if not, you use the current parameter, including the largest task scaling factor, and exit. And you repeat this until no joint limit is being exceeded. The second algorithm, very fast, is you have to build up things in such a way that you find out which is the most relative violation joint, and compute accordingly the task scaling factor, which is the closest possible to the value 1. So the one that will bring back the joint velocity to their feasible range. So let's see some simulation and then an experiment. We have done this on the 7 degree of freedom KUKA lightweight. We have a joint range motion given by the data sheet. So the first joint may rotate between minus 170 degrees and plus 170, the second between plus and minus 120, and so on. From the data sheet, we have also maximum speed, and this is this value are symmetric. So joint, say joint 2 can be between minus 110 and plus 110 degrees per second. And of course, the distal joint may have higher speed. And then we imposed, because this was not coming from the data sheet of the robot, some symmetric bounds for the acceleration. We choose 300 degrees per second square for all the 7 joints. The simulation time, or also the sampling time in the experiment, is 1 millisecond. So this t is used to convert these bounds into current joint limits, current joint velocity limits for the algorithm to work. So this example is the result of simulation, but then we try to do the same also in experiment. The robot has 7 degrees of freedom, is required to perform an hexagon in position in the Cartesian space. So a path, a trajectory actually, so with the timing law, which is an hexagon geometrically. So this requires 3 task variable, because we are living on the 3D space, and we have 7 joints, so we have degree of redundancy equal to 4. Now, in this big table, you see many situations. Along the column, you see executing this task with a speed which is 0.5 meter per second, 1.1 meter per second, 2 meter per second, 4 meter per second. So requiring more and more faster and faster motion. When you move from one segment to the other, your commanded velocity has the direction between the current point and the end point of the segment in the hexagon, and this is a unit vector. Just give the directional cosine of the segment, and the speed is the v, which you are moving from 0.5 to 4. The robot starts from a given configuration, it's all the same, and here you compare what happens in simulation in the first row when you're not having any joint limits. You can do whatever you wish. So you're applying essentially the pseudo-inverse solution, okay? And you see that initially with this configuration, you're not even on the hexagon, so you can see a small segment which is an initial transient error which is being recovered by the presence of a Cartesian controller. So you're not just commanding x dot, but you're commanding x dot desired, this one, plus some k positive gain times the error between the desired x and the current x. And once you are on the path, then you will keep this. So you see that you execute perfectly the hexagon, because once you are on it, because there's no limit, you can do this and you're not saturating any constraint, you have no limits for the joint ranges as well in this simulation. And the only thing that changes is the total time of one cycle. 9 seconds, about 9 seconds, 4.5, 2.2, 1.1 second when you're going very fast. So this is kind of a ground or benchmark. This is the best you could do without constraint. Now you're bringing in the constraint, computed as before from all the limits, joint range, joint velocity, joint acceleration. But you're applying your scheme, so your pseudo-inverse, in fact, without taking care of the possible saturation. And of course, once you saturate, those joints will brought in saturation. The joints which are not saturating are keeping the same value, and you may perform some error. In fact, if you're going slow, so at 0.5 Cartesian velocity or speed, then you take a bit more time. You can see that there's some deformation of the path, and over you will get more time, but the faster you go, the more you're not executing the correct hexagon. You still have the Cartesian controller active, so you don't wander anyway. You try to recover, but in fact, you take more time and you don't execute right the geometric path. If you do simple task scaling, in the sense that we have seen in the previous example, so you're just reducing the speed because you realize that some joints are saturating in velocity, so you speed down, slow down all the joints at the same time. Then you see that you obtain larger times. Still in this side of the hexagon, you're doing some error because this task scaling does not take into account the presence of limits in the joint range, which cannot be scaled. While finally, with the SNS approach, you see that you realize at the different speed, always the task exactly, while satisfying all the constraints. Of course, you will take more time than the original situation. In fact, when you're getting very small, you're getting exactly the same total time. When you're increasing, you may be worse than the situation where you don't use any constraint. You don't include any constraint. But of course, now there are constraints, so you expect that you will be worse. And you're much better than task scaling. Sometimes you're compatible, like here, with doing nothing, but of course, here you have error, you don't have any error. So this is a very good solution. And we would have scaled things if we cannot do all the things together without violating the geometric path. So here is some experiment. So we are doing in the experiment exactly an hexagon with point-to-point times, and we are varying the times needed to go from one corner to the other. And this is assigning 1 second for each side of the hexagon and do simply scaling. You see that the scaling will stop practically the robot in some configuration because it's getting very close to the boundaries. But apart from this, we are doing correctly. And this is the SNS. In fact, it's a fast optimized version of the algorithm, which I'm not describing, but you can find it in the reference. And here you see that the robot is doing the task, stopping at the corner, but not speeding down. Now you see the scaling with side motion requested of 0.5 seconds. And you see again that you have many problems in this area because you're getting very close to the joint range limits. So you have to speed down quite a lot. And now with the SNS method, you see that nothing changes. So you're doing the task, rest to rest for each segment, but at the correct higher speed because you require less time. And now if you go even faster with the intermediate time of 0.2 seconds for each segment, then with the scaling method, you run into an emergency of the KUKA controller, while by properly reassigning velocity to the various joints and staying within the limits, you can do the task exactly. And now a second situation, which is maybe harder to visualize. We have still to do the task, but at the same time, we have a secondary task with the elbow. The elbow should perform a sinusoidal motion, okay? And here, again, you see that more time is needed with simple scaling and with 1 second. And also, the motion at the joint level is partly executed correctly. Now, with the fast optimize the SNS method. You do the task, and you see more clearly a regular oscillation of the elbow while doing exactly the end effector task. And remember that the end effector task is the priority task, and the second one is secondary. Okay, so the second video that I would like to present, and which is also the last one in this lecture, is again partly in simulation, a very fancy simulation, and partly with experiment, in which we have, again, multitask motion control with hard joint constraint and with priorities. So here you see the KUKA in a simulated world, still the 6 points, and here you will see two situations. This is using task scaling, so doing the task, Cartesian task that I described before. This is the only task that the robot needs to do, including the presence of hard joints. And this is at the acceleration level, so we move this method at the acceleration command, and you can see two shadowed images. One is green and one is orange. The green is without self-motion damping, which is something that we need to add when resolving acceleration, redundancy at the acceleration level, and the orange one with damping. And you will see that the damped solution has much less self-motion than the other one. And now we have two tasks, and the second task is to keep the elbow closest possible to this vertical plane. And this is the simulation with task scaling, and you will see that, in fact, the second task is not really perfectly realized. And, of course, you slow down the task as well, while with the SNS, you don't slow the task, and the elbow is much closer to the vertical plane. So the secondary task is executed better, and the primary task is perfectly executed without the need of releasing speed. And now a final experiment. This is, again, in acceleration. There's a linear path that goes through 20 points, which are very close, so it seems like the end effector is going around the circle. And this is, again, the SNS method with self-motion damping at the acceleration level. So the whole idea here is that you do the same technique, but you keep the internal motion limited, because when you're moving at the acceleration, you may have a buildup of joint velocity that does not show up at the level of the end effector of the task, but will bring possibly the robot close to their saturated value. Okay, I think this is it. I will simply show the list of bibliography here. Here is a number of background results that we have mentioned across the presentation, both theoretical and some experiment and simulation. And here you will find the software for hierarchical quadratic programming. This is freeware. And these are our contribution to the topic, starting with very old ones to the most recent ones in 2019. For instance, the torque optimization experiment that I showed you. Thank you so much for listening.